In this video, I will be using neural networks to predict whether a tumor in a woman's breasts is malignant or benign. By the way, a benign tumor is a tumor that cannot invade neighboring tissue, which in most cases renders it harmless. A malignant tumor is the exact opposite. It can spread to the rest of the body and is extremely dangerous. The importance of differentiating between the two is obvious. I'll actually be making multiple models, some with logistic regression, some with softmax regression, some simple, some complex, and more. I will be implementing all of these in Keras. This is a prime example of a classification problem. As the name implies, classification simply involves identifying to which of a set of categories or classes a new observation belongs. In this instance, I will be identifying if a tumor belongs to one of two classes, malignant or benign. Before we start building the model, let's take a brief look at the dataset. There are a total of 32 parameters, of which 30 are input features, 1 is the classification, and 1 is the ID number. The inputs are just a bunch of features and measurements of the tumor. Some of these parameters include measurements of the nuclei of cells in the tumor. Examples of these measurements include radius, texture, perimeter, and area. For more information on input features and even the dataset as a whole, you can visit the UCI Machine Learning Repository, which is where I got the dataset from. There will be a link to the website in the video description. The output parameter, which is the classification, comes as M for malignant or B for benign. In the dataset that I use in this video, I exchanged the B for 0 and M for 1. As usual, it will also be divided into inputs and outputs, and you will be able to access it on my GitHub, for which there will be a link to in the video description. And finally, the ID number. As I'm sure you can imagine, it has absolutely no correlation to the diagnosis, so it is in our best interest to simply remove it. If we did include it, then the model would very likely establish some completely arbitrary relationship between the ID number and diagnosis that doesn't generalize. The datasets in my GitHub already have this feature removed. Next, as I did in the last video, I upload the input and output data by making a new folder, clicking upload, selecting my files, clicking open, and finally clicking the blue upload button. Next, to make a new notebook, I click new, then Python 3. From here, I begin writing the code. First, I import all the packages that I'll be using later in the script. Next, I assign the input and output data to df1 and df2, respectively. After that, I scale the input data. I do this because some features are orders of magnitude larger than others, and it is unlikely that these features are significantly more correlated than others to the output. In general, scaling the data is a good practice. I don't scale the output though, because this is a classification problem, and it wouldn't make sense to scale categorical data, even if different classes are represented by some arbitrary numbers, like, in our case, 0 and 1. In the same way as in the last video, I do this with the .scale function from sklearn.preprocessing. I then split the inputs and outputs into training and testing data, with training data being 80% of the total data, and testing data being 20% of the total data. Note that the data is randomly sampled. From this point, I'll begin developing a relatively simple, or shallow, logistic regression model. Logistic simply refers to a sigmoid activation function. You may be wondering why it is still regression when it is being used in classification. Sigmoid still assigns any possible input to an output, which by the way is between 0 and 1. In order for sigmoid to be used for classification, we must set a threshold. For example, on this sigmoid graph, we could set a threshold here, or in other words, any y value, or output, that is less than 0.5 will be 0, and anything more will be 1. Note that with logistic regression, or sigmoid, you can only be predicting between two classes. For problems with more classes than this, you will have to use softmax regression, which I will also be implementing in this video. With our dataset having two classes, either approach works equally well, as we will see. Anyhow, for the logistic regression model, I first define the model in the line model equals sequential. I then add an input layer with 30 neurons. This corresponds to the 30 input features from the dataset. This connects to a single hidden layer with 13 neurons, which I chose for a completely arbitrary reason. It corresponds to my age. Each of the hidden layer neurons has a ReLU activation function applied to them. Why ReLU, you may ask? Is it not inherent in logistic regression that we use sigmoid? Yes, it is, but not necessarily in the hidden layers. Frankly, ReLU performs better than sigmoid, and logistic regression with a threshold can still be used as long as the output value has a sigmoid activation function applied to it. These connect to a single output layer neuron, which will have the sigmoid activation function applied to it. In this line, the model is compiled. The loss or cost function that is used is binary cross-entropy. The only thing that you really need to know about binary cross-entropy is that it is used in tandem with the sigmoid activation function for two-class classification problems. I used the Atom optimizer, which, as you know from the last video, simply states how the weights are updated, and in general, performs better than most other optimizers. I also state the learning rate, which will be 0.001, and that I want the model to keep track of the accuracy metric. I then define the early stopping function, pass several parameters, assign it to early stopper, and add this as a callback in the .fit function, which is all assigned to history. In the .fit function, I pass several other parameters, including xtrain, ytrain, the number of epochs, which is 2000, the validation split, which is 15%, and verbose, which I set to 0, or false. In the next line, I also assign history.history to history_dict. I will just be using this to plot the performance of the model. For more information in the .fit function, early stopping, and much more, watch the previous video in the series, where I predict the number of views on a YouTube video with neural networks implemented in Keras. If you aren't really familiar with this Keras syntax and you are confused, certainly go back and watch the previous video. Once I cover a particular topic, I don't repeat myself in the same detail, or else this video series would be extremely repetitive. From this point, I plot the training loss and the validation split loss over the epochs. As you can see, the early stopping function did its job. It made the model complete training much faster and didn't allow the model to overfit. Next, I plot the accuracy of the model over the epochs. Accuracy is the inverse of the cost, in the sense that you want it to be as large as possible, whereas you want the cost to be as low as possible. Once again, the graph indicates that the model is performing well. Once I've done this, I want to calculate the loss, and also the accuracy, as a fraction of the number of correct diagnoses out of the total diagnoses for the testing data. I do exactly this in these lines. When I print out the loss and the accuracy, you can see that they are pretty good. Next, I use two other metrics to further reveal the performance of the model. They go hand in hand and are pretty cool. First, I must explain why there is a need for a metric besides the accuracy, which is calculated as a fraction of correct out of total responses. And before I do that, you must understand the differences between true positives, true negatives, false positives, and I'll explain the differences with this chart. True positives are where you correctly predict something to be true. This could be correctly predicting that a tumor is malignant. True negatives are where you correctly predict that something is false. This could be correctly predicting that a tumor is not malignant, or in other words, benign. There are also false positives, where you incorrectly predict that something is true. This could be predicting that a tumor is malignant when in reality it is not. False negatives are where you incorrectly predict that something is false. This could be predicting that a tumor is not malignant when in reality it is. Depending on your intentions, you'll want to maximize certain parameters and minimize others. To illustrate this concept, I will use the diagnosis of breast cancer as an example. A patient for whom this diagnosis is crucial may want to make sure that if she does have cancer, then it will be identified, even if the diagnosis may call for further testing. This patient would want to maximize true positives and minimize false negatives, even at the expense of an increase in false positives and a decrease in true negatives. On the other hand, a hospital with plenty of patients may find it more profitable to raise the diagnosis threshold, so that there are fewer patients without cancer that require costly further testing. This hospital would want to maximize true negatives and minimize false positives, even at the expense of an increase in false negatives and a decrease in true positives. Perhaps the hospital seems evil and even abhorrent to you. Regardless, it would be interesting to see how the model would perform in both of the situations and many more in a single graph. That is exactly what a ROC curve does. AUC is the area under the curve, and it is a numerical value that tells us how well the model would perform in different situations, like with the patient and the hospital. The ROC curve essentially plots the possible thresholds of a trained model. It is created by plotting the true positive rate on the y-axis against the false positive rate on the x-axis. The rate for true positives is the number of correctly predicted positives out of all the actual positives. The rate for false positives is the number of incorrectly predicted positives out of all the actual negatives. Let's see how an ROC curve would be created. For the first point, say that the threshold was at 0.3. Any probability below 0.3, and the model would predict that the patient has a benign tumor. Any probability above 0.3, and the model would predict that the patient has a malignant tumor. This threshold is, relatively speaking, pretty sensitive, meaning that if the model's diagnosis is benign and not malignant, then it is most likely that the correct diagnosis is also benign. This threshold would best suit the heartfelt patient in the scenario from before. Perhaps with this threshold, 210 out of the possible 212 actual positives were correctly diagnosed as malignant tumors. So, the true positive rate is 210 divided by 212, or about 0.99. Unfortunately, with this threshold, the model may incorrectly diagnose 55 out of the 357 actually benign tumors as malignant. So, the false positive rate is 55 divided by 357, or about 0.15. This coordinate pair would then be plotted on the graph. Next, I will use a threshold of 0.7 and calculate the corresponding true and false positive rates. In contrast to 0.3, 0.7 is a specific threshold, meaning that if the diagnosis by the model is positive, it is most likely that the correct diagnosis is also positive. This threshold would best suit the lucrative and amoral hospital in the scenario from before. Perhaps with this threshold, only 190 out of the possible 212 actual malignant tumors are correctly diagnosed. The true positive rate would then be 190 divided by 212, or about 0.9. In addition, with this threshold, the model may incorrectly diagnose only 4 of the 357 actually benign tumors as malignant. So, the false positive rate is 4 divided by 357, or about 0.01. This coordinate pair would then be plotted on the graph. The process would continue in a similar fashion, only starting from a threshold of 0 and working upward in much smaller increments. As far as AUC, you just need to know that a perfect model would have a value of 1. An ideal model would look something like this. A model with whatever threshold was used to generate this point wouldn't have to make any compromise in order to please both the patient and the hospital. By the way, the conflict between the patient and the hospital is known as sensitivity versus specificity. In my opinion, this is not only interesting from a technical perspective, as a programmer or a data scientist, but also as a moral consideration, seeing it from the lens of a philosopher. Anyhow, back to programming. In these lines, I calculate the AUC and plot the ROC curve. In order to do this, I first import these two packages from sklearn.metrics. Then, I calculate the model's predicted outputs for x-test as probabilities, and then assign these values to y-test predictions. It is important that the predictions are probabilities and not just zeros and ones. Remember, in order to get the AUC and the ROC curve, you need to change the threshold. If your predicted outputs were categories represented by zeros and ones, then the threshold was already set, likely at 0.5. Attaining the AUC and the ROC curve with different thresholds from that point would be impossible. However, I actually didn't need to include the underscore prova, as model.predict defaults to probabilities. I did this simply to emphasize the fact that probabilities are needed for the predictions. So, model.predict classes would not have worked. In the next line, I calculate the false positive rates and the true positive rates at different thresholds. Note that the thresholds are actually assigned to a variable. In the next two lines, I calculate and print the AUC. In these lines, I graph the ROC curve. As you can see, the model is pretty darn good. I then repeat this process for the training data. Once again, it performs well. I can now conclude that I have a functioning model. Remember that in this implementation, I used sigmoid as the activation function and binary cross-entropy for the loss. This model would be considered a logistic regression model and is just one approach to a binary classification problem. As promised earlier in the video, I will now implement a different approach to the same problem. This approach involves the softmax activation function and categorical cross-entropy as the loss. By the way, this approach, which would be known as softmax regression, can also be used in multi-class classification problems, while the simple logistic regression can't. So, without further ado, let's implement it. From the start, things actually start to get different from the last implementation, and the last video for that matter. I use the function toCategorical from keras.utils, pass ytrain, and assign it all to ytraincat. What toCategorical does is it converts a class vector to a binary class matrix. Okay, what does that mean? Well, a vector is simply a one-dimensional array. This is the original ytrain, a vector. Note that besides the zeros and ones, there are also indices. A binary class matrix, or what toCategorical makes ytrain, is simply a bunch of rows and columns made up of binary numbers, where each row represents a class. Let's take a look at what ytrain looks like after it was passed into toCategorical. Here, the first row corresponds to the first value of the original ytrain. How is 0, 1 equal to 1 and 1, 0 to 0? Well, 1, 0 represents the first class, which is 0, and 0, 1 represents the second class, which is 1. The same applies for any two corresponding data points in the original and current ytrain. To further solidify this concept, let's see how this would play out with three possible classes. Let's say that the classes were originally expressed as zeros, ones, and twos, and that the first four data points are 0, then 2, then 1, then 1. Assuming that 0 is the first category, 1 is the second, and 2 is the third, after passing 0 into toCategorical, we would get 1, 0, 0. After passing 2, we would get 0, 0, 1. After passing 1, we get 0, 1, 0. And again, after passing 1, we get 0, 1, 0. The reason why I did this is that the activation function, softmax, and the loss function, categorical cross-entropy that I use, requires data in this format. I'll talk about the activation function and loss function a bit more in just a second after we define the structure of the model. In these lines, I do exactly this. First, I define the model in the line model equals sequential. Then, I add an input layer with 30 neurons. This corresponds to the 30 input features from the dataset. This connects to a single hidden layer with 13 neurons, which again I chose simply because it corresponds to my age. Each of these neurons has the softmax activation function applied to them. These neurons then connect to two output neurons instead of one in the logistic regression model. With the softmax activation function, this is simply the necessary formatting. The format, as you may have noticed, corresponds to the training data after toCategorical was applied to it. toCategorical was used to match the training data to the format that the model's outputs would be in. This allows us to train the model with the training data, which is obviously a crucial step in machine learning. In my code, I don't apply toCategorical to ytest and assign it to ytestcat just yet, but you very well could. Eventually, you'll need to do this in order to calculate the loss and cost of the testing data. Before I train the model, I first define the loss, which is categorical cross-entropy, the optimizer, Atom, and the learning rate, 0.0001. Atom was already explained in the previous video, but categorical cross-entropy is new. All that you need to know about it is that it is used in tandem with softmax for multi-class classification problems. Next, we train the model with the early stopping callback, assign it to history, and assign history.history to history_dict. After that, I plot the training loss and the validation split loss over the epochs on one graph, and the accuracy over the epochs on another. As I did last time, I also calculate the loss and accuracy of the model with the testing data. Note that this time, I have to apply toCategorical to ytest, because we are using softmax regression. Already, you can see that the model is pretty good, just as it was with logistic regression. Still, I continue measuring the performance of the model with the AUC and the ROC curve. I first define them for the testing data. I do that in these lines, and once again, they are pretty darn good. When I do so, note that I use the original y-test and not y-test-cat, because this is the required format. I do the same for the training data, so I use the original y-train. Again, the model performed well. We can now safely say that in this instance and with this particular problem, it doesn't really matter if we use logistic regression or softmax regression. In this script, I proceed to modify the number of hidden layers to see if it will improve the performance of the model. So, I define a model with 30 inputs, 4 hidden layers each with 13 neurons, and an output layer with 2 neurons. Each hidden layer neuron has the softmax activation function applied to it. I train the model over 3,000 epochs with the early stopping callback and plot its loss and accuracy over the epochs. I then calculate and print the loss and accuracy as numerical values. I also find the AUC and the ROC curve. In conclusion, it doesn't change the performance of the model. Before concluding the video, I want to address an issue that someone in the process of developing a model would face. The problem is the following. How can you tell if your model would benefit from having more data? My preferred approach would involve a visualization and is known as learning curves. It involves restricting the amount of data used a lot to train the model, then calculating the performance, increasing the amount of data used slightly, then calculating the performance, increasing the data used, then calculating the performance, and so on. This data can then be graphed, with the number of data points used on the x-axis and both the training and testing accuracy on the y-axis. As the amount of data used increases, the training accuracy shouldn't be impacted much, and the testing accuracy, at least initially, should increase. If the testing accuracy follows an upward trajectory in the latter half of the graph, then it would most likely benefit from more data. If it remains constant or decreases, then you can assume that the model will not benefit from having more data. I implement such learning curves in these lines. By the way, linspace creates a defined number of equally spaced values in a defined range. I use it here to determine the different fractions of the training data that I will use. As you can see from the resulting graph, increasing the amount of data used in training would most likely not have any effect on the model's performance. I mentioned this in the last video, but there are many ways in which programmers improve the performance of neural networks. Among these are batch normalization, dropout, and weight regularization. For this model and for this dataset, after implementing these, there is no noticeable improvement. If interested, the supplementary code on my GitHub contains the implementations of each of these. So there you have it. Functioning logistic and softmax regression neural network classification models implemented in Keras. In case you didn't already know, this video is part of a series in which I find really cool datasets like this one, and for each of them I show you how to implement a neural network. In doing this, I hope to both entertain and educate you. Subscribe and click the notification bell to be notified when I release the next video in this series, and also hit the like button and leave a comment if you want this video to reach more people.